Here comes another assumption. We assume that all uncertainty sets are zonotopes. Zonotopes in their classical definitions are affine transformation of hyperboxes, which are denoted by C and G, where C is the offset term of the zonotope, is a vector, and G is a matrix, it's called the generator matrix, which is multiplied by a box to generate symmetric shapes as seen in examples in this picture. Often it is not a bad assumption that to assume all our uncertain sets are zonotopes. It's actually not necessary for the technicalities in the paper, but we use assumption for computational purposes. Also, zonotope order reduction methods, which are standard methods for reducing the number of generators in a zonotope, become very useful in solving the optimization problems later to reduce the size of the optimization problems. So I would claim that having zonotopes actually helps and is a big part of our paper. Now it is the time to pick values for M, N, R, and S. We can pick any values, just the error terms depend on them. So it makes sense to pick values that minimize the error terms, and we do it in a way that we minimize the Frobenius norm of the zonotope generators of these errors. And actually that leads to a standard least squares problem, for which we have a closed form solution for M, N, R, and S. And it's just the most significant computation required here is taking a pseudo inverse of a large matrix, and that's all. And it's quite convenient to do. Now here is the second main idea in this paper, which is the parameterization of the controller. So our controllers are proposed as affine maps of the history of errors occurring in the output predictor system. So U at time t is U bar, which is a term that we have to choose, plus theta, which is a gain matrix that is also a parameter that we have to design, times the history of errors of the system, which start with the initial output and all E0, error at time 0, all the way up to ET plus minus 1. And just note that at time t, all these error terms can be observed from the output predictor system, because the outputs of the system can be observed, and we have M and N matrices, so we can compute these error terms. Using this parameterization, the system response can be also cast as a affine transformation of this history of errors, and actually it can be shown that the system response becomes linear in control parameter. This is the key to our computations in this paper. We shall note that the size of the theta matrix and the phi matrix here become larger and larger as the time history goes up. And so these matrices are actually becoming fatter and fatter. Actually, there is a way to control this. We can choose the length of the history that we want to play with. We want the system controls to be a function of. So it's basically saying that we can choose arbitrary number of theta entries to be 0. And that is something that we can choose, just it may downgrade the performance. The control parameterization in the last slide is very similar to disturbance feedback idea that is used in state feedback schemes, where the idea is to use linear or affine maps of the history of disturbances acting on the system as the controller. However, extending this idea to output feedback, which is the main one of the main contributions of our paper, is not immediately possible because we cannot measure measurement noise and process disturbance in a partially observed environment. But the key is we can actually observe error terms, because those error terms are coming from output predictor system, and everything in the output predictor system is observable. So here's the main idea. Instead of disturbance feedback based on V and W, have the disturbance feedback on E, which I call it error feedback instead of disturbance feedback. So finally, after the controller parameterization and parameterization of phi in terms of theta and all those linear encodings of the system, and also linear encodings from polytom containment problem, all the system being linear, the whole policy synthesis optimization problem, which was originally min-max problem, becomes a linear program. And we can solve this program to obtain numerical values for theta and u bar, which are our control parameters, also system response. As our first example, we compared our method versus LQG. LQG is, of course, optimized for Gaussian noise and disturbances. In case we replace them with zonotopes, we found pretty comparable performances, with the difference that as the dimensions went higher, LQG was fragile and failed, versus our method was better in comparison. In the pictures here, you see the poles of the systems that were randomly generated. As you see, some of the poles are out of the unit circle, indicating the system was not stable. And the shaded areas on the pictures on the right are the reachable sets, for the yellow for the performance outputs, which is the first state, and the purple one for the controlled inputs. As you see, the red one, which is our method, always remains in that set. And as it indicated, the sets are quite conservative. As our second example, we consider the constraint control problem, where our system has 10 states, it's unstable, and it has hard constraints on its first two states and control inputs. As you see, the specification was getting those two states into a red rectangle at the end of the horizon, which was 20. And for all those times, the control inputs had to be bounded into the blue region. And as you see, we solved the optimization problem, and these are the random trajectory with the reachable sets associated with it. As you see, the specification is met. It's actually also worth to note that on the picture and the animation on the left, the reachable sets initially grow because the system has 10 states, lots of unobserved states. But as the observations kick in, the reachable sets shrinks because there are more information coming. This is a reminder of how adaptive control works, and actually our next example is about adaptive control. The idea in this example is that our system can have fixed but unknown parameters, and that those parameters can be incorporated as part of the state if they enter the system linearly. And once we do the robust optimization with respect to the parameters, and if the robust optimization problem is of course feasible, then we obtain a correctness certificate. And this idea is similar to what people do in robotics and reinforcement learning and domain randomization. As an example, here you see on that picture on the right, a corridor of yellow obstacles with a particle which has a double integrator dynamics in the vertical direction and moves in the horizontal direction with a constant velocity. Actually, in the vertical direction, there also exists some noise in the measurements of where these obstacles are. But the environment that generates these obstacles is mathematically characterized by a set of polytopes. So once we design our controller to be robust versus all of these polytopes, then we have the certificate that the system is going to work under all possible environments. And these three examples are just three randomly generated environments. The optimization problem was solved offline for all environments. As our last example, we consider extension of our finite time synthesis work to infinite time synthesis. If our system is t-periodic, which means the dynamics repeats itself after time t, then if we can get a controller that also our initial state gets to itself or shrinks itself after time t, which can be cast as x at time t, the set of states at time t would be a subset of set of states at time 0, which become an instantly polytope containment problem added to the optimization problem. Then, by repeating the same controller from time 0 to t for the next t episode, we can satisfy the constraints for all times. And this can be very useful to periodic systems, like, for example, in this example, we have a compass gate, where there are two legs moving in the horizontal direction. As one touches the ground, the other swings, and until it touches the ground, and the swing and stance leg change. And the only measurement coming here is the difference between these angles, the angles of the hip, and with just this, and also with the noisy measurements of that, we designed the output feedback controller to stabilize the movements, and you see the results on the picture on the right. And this concludes the presentation of the paper. Please find the link to the paper and the associated code. And if you're interested in have any questions, please don't hesitate to contact me with my email address at sadra@mit.edu. Thank you very much.